Visions. It's on graphene, okay? And the second part, we're preparing a paper, beginning to prepare a paper. It's on silicon nanowires, and you'll see. So first let me talk about the atom probe. It's a field ion microscope plus a special time-of-flight mass spectrometer. Maybe it's better I come out here. Yeah. And this instrument, as I'll show you, basically can look at all materials. If you want a short primer on this book, there's a special issue of the MRS Bulletin, October 2009. And the key to its success of being able to look at all materials is that we use a picosecond UV laser to dissect specimens, essentially one atom at a time. That's a key aspect of the instrument. And it's called a LEAP. The commercial name is a LEAP, Local-Electrode Atom Probe. And the generic name is Atom Probe Tomograph. And it's a unique instrument because you can map out the positions of atoms in three-dimensional space, in direct lattice space, and you can determine the chemical identity of each atom that you detect. And it has single ion sensitivity, this mass spectrometer. The instrument, the original instrument, the field ion microscope, it dates back to 1955, the first observations of atoms on the surface of a specimen. And this is a simulation of a specimen, and basically it's a curved surface, and you can see individual. Is it better? There's a lot of feedback. Okay, so here is a simulation, as I said, and the atoms in red are the ones that you can see. And when you look at this, when you look at the atoms that on a monitor, basically it's a stereographic projection to first order. And helium atoms are the messenger that tell you where the atoms are sitting. And the helium atoms are highly polarized in the electric field, and they have a very high effective temperature. So when they hit the tip, basically, they bounce several times on the tip to slow them down, to accommodate them to the surface temperature, which is around 30 Kelvin. And then they're ionized a few angstroms above the surface. So each atom has a cone of helium atoms that give you a signal, and you can see the atoms in real space. And forget about the right-hand side with hydrogen. So the key points are of the atom probe, you determine the positions X, Y, and Z in real space. And from conservation of energy, you can determine the mass-to-charge state ratio. And so what you measure is the effective voltage on the tip. This is the charge on the electron. This is the time of flight. And this is the flight path. It's basically the second technique that was used to discover isotopes. The atomic resolution in depth is equal to the interplanar spacing, HKL, and that can be less than 1/10 of a nanometer. The lateral resolution depends on the specific crystallographic plane you look at, and that's between 0.2 and 0.4 nanometers. The current detection efficiency is between 50 and 60%, 57%. And the whole basis of detecting the atoms, the ions, or the atoms, is this microchannel plate. Maybe I don't use this at all. Can everyone hear me? Yeah. Oh, you need it for the video? Oh, yes, that's right. Just show the slides. It's very microphonic. So let me just show you an example, a cartoon of how it works. There are no helium atoms in when we do this. It operates under ultra-high vacuum. And this is a multi-layer specimen. This is a multi-layer specimen consisting of red atoms and blue atoms with a sprinkling of green atoms. And this is the detection system here. The vertical plate is the detection system. And then you pulse it with the laser light, and you can see the raw data. And this is approximately what you see on the monitor during the course of an experiment. And the curvature of the planes is a geometric artifact. And then you reconstruct. And there's your multi-layer, which it's really, this is 2 dimensions. You reconstruct it in 3 dimensions. Okay, and here's another cartoon showing how it works. This is the so-called local-electrode here that you're looking at here, this conically shaped device. These are silicon nanowires, say, a little bit of gold on the top, the gold catalyst, and then you evaporate. You hit them with a laser light, and you can see over here what happens. This is the potential energy of an atom at the surface, and it's field evaporated over this Schottky hump, and it becomes ionized. And then you collect the mass spectrum. Every time it hits the detector, the output is a mass-to-charge state ratio, and you count and you can identify the isotopes. And here's a simple example for silicon-boron alloy. And you can see the 3 isotopes of silicon here in the doubly charged state. You see the 2 boron isotopes in the singly charged state. And here you see boron in the doubly charged state. And you can, if you look at the background here, this is counts per channel. It's quite low, 10. And that's the reason you need ultra-high vacuum, because you want the number of counts in the background to be as small as possible, so you can see very small peaks. And we're able to detect concentrations in certain cases as small as 7 atomic parts per million. And the mass resolving power, say, for this is for aluminum, 27. It's about full width 10th maximum is about 500, and the full width half maximum is about 1,000. And I already said this. The white noise is about 10 counts. Okay. Now I'm going to talk about the first of 2 topics, and this is graphene. And this was a result of an interaction, a visit by a Jayan from Rice University, and asking the question, do you think you could look at graphene? So he and his group supplied all the graphene to us, and it was all grown on copper, as I'll show you, on pure copper. And this is the graphene over here. This is a scanning electron microscope image of the graphene. And you can see regions here that are monolayer graphene and regions here that are bilayer. And then in the background, you can see the copper foil. And this is the Raman spectrum, which they took at Rice. Okay, now this is a TEM micrograph of this tip, and I'll explain to you in a second how we prepared the specimens. But this is the copper foil here on the left-hand side. Here is the graphene layer here, and then here is the nickel, which is deposited on top. So you have a sandwich then, which consists of copper, graphene, and nickel. And over here is the graphene, and it's we use a carbon iso concentration surface of about 9 atomic percent to define the graphene. So you see all 3, and it's broadened, and I'll talk about that a little bit also. So here's how you make the specimens. This is I showed you this one already. This is the SEM micrograph. And then on top of the specimen, nickel is deposited. And then with the dual beam fib microscope, we mill out a specimen that has a triangular cross-section. So it's a wedge-shaped specimen, and you pick it up here with an omniprobe, and then here is that same piece over here, and then we use what's called an arm, ARM, and that allows us to rotate the specimen and align the interface such that it's along the long axis of this nanotip. Okay, and we can also put it on a TEM grid, the specimen first, to analyze it using transmission electron microscopy, and then go from here to here, ion mill it into the shape of a nanotip, and this is your specimen. And you can see the nickel side, the copper side, and this dark line here is the graphene. Okay, now here is a plan view of the graphene, and you have an isoconcentration surface, once again, of carbon defining the graphene. And you can see there are regions here that differ from most of the specimens. And these are regions that are low in carbon, and what we see chemically in those regions is oxygen, OH, and CO2. And if you look at the mass spectrum of, say, this region over here, this is what the mass spectrum looks like. Well, nickel and copper you're going to get, of course. And you see carbon dimers, singly charged, and then you see carbon trimers, and then you see carbon monomers, and then you see in the singly charged state, and then you see carbon in the doubly charged state. There's a little bit of hydrogen, not much in the background. And then if you look in the region here, these regions here that look to be like amoeba-like regions, you'll notice what you see is you see CO2, CO, carbon monoxide, and once again, you also see these dimers, trimers, and then monomers of carbon. So you can get a complete chemical analysis of the specimen, the region where it's essentially pure graphene, that's at the right density, and these regions which is lower in density than the graphene. Okay, now this is a little bit more complicated, this slide. If you look at this, this is a cross-section, and you see here nickel, copper, and graphene, and the interface is broadened. And this is in the graphene, and then this one over here, this is a plan view, but in the regions that are carbon deficient. And then if you look down here, you can see concentration profiles. So these are concentration profiles in atomic percent. And if you look at this first one, these are what we call decomposed ions. So you're seeing carbon, oxygen, and hydrogen. And you can see the biggest peak, as you would expect, is the carbon peak. There's some oxygen also, and also a small amount of hydrogen. And over here, you see these molecular ions, but they exist in the pure graphene also, but they're at a lower concentration. If you then look at this region, which is carbon deficient, you can see that the oxygen concentration is much higher, and the hydrogen concentration is much higher. And also, the molecular ions, they're much more abundant. They have much higher concentrations. So in this way, we have a chemical map of the graphene, both the essentially graphene that's at the right density and graphene that's at a lower density. This work is not ours. This is from fairly recent literature. When you grow the graphene, the partial pressure of hydrogen and the partial pressure of oxygen are quite important. And the key point is here that for small oxygen concentration, you get hexagonal-shaped regions like this. And for a high hydrogen pressure, you also get hexagonal-shaped regions like this. And the exact morphology that you get of the graphene depends on the hydrogen partial pressure or the oxygen partial pressure. Okay, so in summary, what we did is we looked at CVD-grown graphene on a copper substrate. We analyzed it with atom probe tomography, and we're able to get both plan view and cross-sectional views. And we can see how the oxygen and hydrogen are distributed between the regions that have the right carbon density and regions that are carbon deficient. And we're looking at monolayer graphene. And so what we have is a atomic scale portrait of all the chemical elements that are involved. And I think, and I hope, that this atomistic evidence for characterizing graphene can be extended to other two-dimensional functional materials. So that's the graphene part. And we submitted that for publication, and we just resubmitted the revised paper. Okay, so this one is on silicon nanowires, non-uniform dopant distributions in ex situ boron. These are grown by an ex situ technique developed at the Hebrew University by Ro'i Yerushalmi and his students. This is the reference down here in science. And the graduate student that's working on this at Northwestern is Mr. Sun, and Lincoln Lahone and I are supervising him. And Yossi Rosenbachs is also involved in this research doing electrical characterization. So we have 1, 2, 3 institutes involved. Okay, so this is just a schematic of what's done. The silicon nanowires are horizontally sitting on, say, this substrate. So this is a substrate. It's the source of boron. So it's silicon, and it's doped with boron to the level of 1 monolayer. And then on top of the silicon nanowires, which are sitting here horizontally in parallel, you have the phosphorus source, and then you form this sandwich with the silicon nanowires in between. And the objective is then to create PN junctions along the whole length of these silicon nanowires. And this is just a schematic of what's happening on the boron side. You can see the source here corresponding to 1 monolayer. It's an organic compound that produces a 1 monolayer of boron. And then it can diffuse in when you heat it. When you do rapid thermal annealing, you can heat it. And this is a simulation of the distribution that you would expect. This is the phosphorus, and this is the boron. At this temperature of the rapid thermal annealing, the diffusivity of the boron is 1,000 times greater than the diffusivity of the boron. And this is from Roy's group. And this is his graduate student, Ori Chazut. Okay, once again, the real game changer here for us has been using the dual beam fib. In this case, let me just show you the bottom line first on the right-hand side. So if you look here, this is a cross-sectional SEM image. And here you can see this horizontal nanowire, and this is the region. And you see it's sitting on silicon. And then you have silicon dioxide over here, maybe about 4 nanometers thick. And then you have zinc oxide, which turned out to be important. And that was done by atomic layer deposition at argon. And then on top of that, we then deposited platinum on top of that. And now if you look over here, this is the this is the atom probe image. And you can see the cross-section of this same silicon nanowire in the specimen. And this is the end product here. So you have a nanotip with this silicon nanowire sitting this way into the board, a section of the silicon nanowire. And I'm not going to go through these steps again, but I just want to emphasize it would be impossible to do this without a dual beam fib. So for this field, as well as for other fields, the dual beam fib is a real game changer. Before this, we were really restricted to just making specimens, nanotips, using electropolishing. Okay, here are the results. So all the experimental results I'll show you are a result of rapid thermal annealing at 970 degrees C for 20 seconds. And what I'm going to show you are concentration profiles in the silicon nanowire. So here's the distribution of phosphorus, and here's the distribution of carbon, which comes from the organic precursor, and here's the distribution of boron, which is more or less uniform. And you can see that the phosphorus and the boron, the phosphorus and the carbon form a shell. And the reason for that is, most likely, is that you're getting strong segregation of these two elements to the surface. And so because they decrease the interfacial energy, the surface energy, and now phosphorus and carbon have very high surface diffusivities. That's important. Okay. Now, if you look over here, this is a scanning tunneling spectroscopy image, and you'll see it looks different from the atom probe tomographic results. And the reason is that in the atom probe tomographic results, we see both the electrically active and the electrically inactive dopants, whereas in scanning tunneling spectroscopy, we only see the electrically active dopants. So you can see there's a significant difference between what you get from the APT and what you get from scanning tunneling spectroscopy. Okay, now let's go a little bit more detail now. This is the y-axis, and this is the z-axis. So here is your nanowire, and here's the phosphorus source on top and the boron source on the bottom. And these are concentration profiles. So this is concentration versus Z. Concentration versus Z. And you can see over here in this one, you see the silicon, and you see the zinc oxide. Okay, so the silicon is here, the zinc oxide is above it. So let's look in more detail. Okay, this is just the phosphorus. This is just the phosphorus. This is just the boron. And this is just the carbon, and this is just the boron atoms. Each spot is an individual atom. Okay, now you can create from this concentration profiles. So these three concentration profiles are from the phosphorus side of the nanowire. And if you look carefully here, this is the zinc oxide region, which comes from the ALD layers. This is the silicon dioxide, and this is silicon. And you see the purplish kind of atoms, they're phosphorus atoms, and these are its profiles. And it's sitting at the interface, the peak is at the interface between the silicon dioxide and the silicon. And then down here, you can see the boron atoms, which are more or less uniformly distributed. And then you see another peak here due to the carbon atoms, which are sitting in the silicon dioxide layer. Okay, so that's from the phosphorus side. And now if you look at these same guys from the boron side, you see the phosphorus is uniformly distributed. And you see over here this peak due to the carbon atoms sitting at the zinc oxide silicon dioxide interface. And then you see a small peak here due to the boron atoms sitting in just the silicon dioxide. Okay? So those are the main results. Now here is a cartoon explaining those results. This is the phosphorus source, the boron source. The boron atoms are this kind of bluish color. The silicon atoms are the kind of grayish color here. Here's the silicon atoms, the silicon atoms. So this is a blow-up. This region here is a blow-up of this region. And this region here, this is a blow-up of that region. Okay, if you look at the two species, if you look at this species, these are the carbon atoms. They're diffusing like this. They have a high surface diffusivity. And similarly, here are the phosphorus atoms at the interface between the SiO2 and the silicon. Whereas if you look on the boron side, you can see this flux of carbon atoms at this interface between the SiO2 and the zinc oxide. And then over here, you see this flux of boron atoms into the silicon nanowire, and they're more or less uniformly distributed. Okay, so what have we done here? In summary, we've investigated these dopant profiles for Pb, phosphorus boron. Originally, Mr. Sun had written this BP, which I said is beyond petroleum, BP. Okay, so these are co-doped, and they were analyzed by atom probe tomography. And the phosphorus and the carbon atoms are enriched in the surface at the interfaces. Boron is found more or less uniformly distributed in the core of the nanowire. And you can explain this because both carbon and phosphorus have high surface diffusivities. They're preferentially segregated at interfaces. And this is what gives rise to this non-uniform distribution. And finally, the bottom line, of course, is that it's a powerful way for looking at overall dopant concentrations, which are both neutral and charged. So the combination of the two techniques, STS and atom probe tomography, give you a fairly detailed picture. Okay, I'm going to stop here. That's it.
Thank you, David. Any questions? So the graphene, I would assume, is atomically thin initially after growth.
Yes.
And yet, if you look at your carbon cross-section,
right.
It's over order of magnitude larger.
Right.
So is that an artifact of the sample prep?
No, it's not an artifact of the sample. It's because the three materials, the graphene, the nickel, and the copper, have different evaporation fields. And so you get trajectories when the atoms are evaporated that tend to broaden it. So it's an artifact. It's an artifact, but it's an artifact of the technique that it's not an artifact of the preparation. I mean, we've seen this in other materials, too. It's not the first time. So it wasn't a surprise to us. It happens even in metallic alloys, where we know, say, from TEM, how thick it should be, and it's always somewhat broader. And the amount of broadening it's material dependent. I mean, there's no.
But the chemistry, which is what you're
Yeah.
primarily interrogating, how can you be confident that that's not affected by the sample prep?
You mean for this particular case or in general? In this case,
In this case.
all I can tell you is this case is a bit harder because, say, with metallic alloys, you know what the bulk compositions are, okay? And here it should be 100% graphene. And the positive point is that the density is correct for the areas that are a monolayer and 100% graphene. But for these areas that are kind of amoeba-like in shape, those are always deficient in carbon. Instead of being what graphene's around 36, and we get around 32. So
I'm just wondering if those amoeba-like regions are induced by the deposition, subsequent milling,
yeah,
et cetera.
that would be hard to say. It would be hard to identify which one. In an absolute sense. Are we on? Oh, you're on. Ah.
And back to that slide for this here. Yeah. So I understand the atom probe part. I'm not sure I understand how the bias-dependent STM was taken here. Is it the same sample, the different sample?
Oh, this is a different sample. This data was supplied by Roy E., but he uses the same prescription here, 970 degrees C for 20 seconds.
But what are we seeing here?
Oh, you're seeing the distributions. Just like here, you're seeing the distribution of boron, which is uniform. And here you're seeing the boron. And here you're seeing the phosphorus. I'm sorry. And then there's a scale on the side here, which gives you the concentrations in number per cubic centimeter. And these are the electrically active elements, right? Electrically active boron, electrically active phosphorus. And
How did he obtain it?
what?
Okay. We'll talk later.
Okay. Whereas these include both electrically active and electrically inactive. So the atom probe gives us the total amount, whereas the STS only gives you the electrically active
No,
component.
I'm just interested in geometrical setup.
Okay.
Ariel.
I guess that carbon, we have carbon source from the preparation and also from the materials that we're using. So one way to test only the graphene would be by preparing a single-layer graphene made out of C13 atoms. That can be done slowly. So then you can be sure that you're testing only the graphene.
That you have 100% graphene. Yeah. Yeah. I mean, also in answer to Mark's question, no one has looked on this scale before, too. So when you look on a fine scale very often, you see things that you don't see when you look on a coarser scale.
Yeah, I guess the core concern I have is that the sample preparation may be changing in particular chemistry.
Well, you know, the samples were made by a Jayan and not us. So, and he's done.
When they're grown, there's a lot of understanding, but then the subsequent deposition, I guess the nickel, followed by.
You mean the deposition of the nickel? I mean, they're grown on copper, right? And then we deposit from a sputter source. Yeah. It's low energy sputtering. I don't know. So, I mean, the ions hit the atoms are sputtered from a nickel source, and then they hit with a rather low energy on the graphene.
It's a nickel source?
Yeah.
So it's a nickel field?
No.
Well, what are the, is it gallium atoms or?
No. So there's two things involved here. Let me go back. Okay. In this process, I'm sorry. This is for the graphene. I have to go all the way back to the graphene. Okay. So here's the graphene layer. This is an SEM picture, and it's grown on copper foil. And then we make a sandwich by depositing nickel on top of this. So you have a sandwich here, and this is the nanotip that we look at. So the graphene is sitting here, here's nickel, and here's copper. And then this is how we make a tip. We do combined TEM and atom probe tomography. So we take a specimen without going through the details, and we transfer it to a grid and look at it with the electron microscope. And then similarly, we can take the same specimen and we can make an atom probe tomographic tip out of it. And that requires using gallium ion milling. And with the gallium ion milling, we start at a high energy, and then we finish at just maybe 2 kilovolts of energy.
Okay. So I suggest if you have more questions, let's skip to the coffee break afterwards, so we'll be on time. The next speaker will be Professor Yossi Rosenberg.